Hi, my name is Doug Wagner, and I'm an instructor in the Faculty of Engineering and Applied Science at the University of Regina. And today I'd like to talk to you about convergence and how convergence applies to the world I work in. I'm coming to you from the University of Regina, which is located on the ancestral lands of several First Nations communities, which are governed under Treaty Number 4. So to continue talking about convergence, I'd like to take you to our power lab. So here we are in one of our undergraduate labs in the Faculty of Engineering. And this is our lab dedicated towards power equipment and power systems. Some of the work that I've done in terms of research work has been related to this field. And in this area, I have to consider this concept of convergence. So this equipment you see here is tied to a variety of functions, primarily to protect our power system in order to keep the lights on. It's worth mentioning that in electronic systems engineering at the University of Regina, when we talk about electricity or electronics, when we're looking at this, it can take the form of either electrical power, where we're doing some work. We're either providing heat for a process, or we're more often than not turning a rotational device to do some useful work with that electricity. Or we can also use electricity, or specifically in electronics, to convey information. This can be across media or devices, or through a distance. So in our program at the University of Regina, we have focus areas in our electronic systems engineering program. We have microelectronics, controls and automation, communications, and the area I work in, energy and power. So in keeping the lights on, we have to make sure that we can protect the electrical systems when a fault occurs, and many occur primarily due to weather, other times equipment failure, and we respond quickly and efficiently and reliably to make sure that we're able to maintain a reliable power system. Why does convergence matter? So this device that we have here on the screen is an integrated electronic device which provides protective functions in our power system. It's measuring currents, voltages, frequencies, all things which are important to ensure that we're able to deliver reliable power. But to do that, this device is interfacing to our electrical system, and it's achieving its functions by relying on microprocessors, field programmable gate arrays, and the know-how to program those systems. We see the convergence of these differing areas in this equipment we're using. To use it effectively, we need to understand these different elements as they come into play. But wait, there's more. We can take advantage of the fact that units that we have for our protection can also communicate with one another to provide a more reliable and timely response in the event of power outages. So we do that by involving communications equipment. So we network these devices, much as we would see networks in buildings and in homes, to provide fast communication that also has to be secure to provide this function. So we see an additional level of convergence of different technologies, and understanding how convergence plays into these systems becomes important for us as we learn about this technology and how to effectively use it. My particular work involved overcoming one of the limitations of equipment such as this in terms of the amount of time it takes to measure and determine what the amplitudes or the signal levels of those currents and voltages are, so we could respond faster to faults in our power systems.
I'll never get hired as a camera operator. So back to another segue. So let's talk about traveling wave fault detection. So first, we're going to look at a conventional way that we determine the amplitude of our currents to determine if we have a fault. In our power system, we have an alternating current, which is operating at 60 cycles per second, or 60 hertz. And that can be described by a function that looks like VP, which is our peak voltage, some sine function, which is operating at a radian frequency, and some angle. And the time between this one cycle is about 16.67 milliseconds. So that's the amount of time it takes for one cycle to pass on our power system, and it takes us at least half of that time to convert this signal from its amplitude into a digital form that we can measure. Is there a faster way? And the answer is yes, there is. So we can build on the area of electromagnetics and an area in physics known under the moniker Maxwell's equations, and we can look at traveling waves. And our traveling wave theory comes from the area of communications and physics, but it allows us to pick up the discontinuity or the transient that occurs during a fault in our power system. And this is moving at a speed very much faster or taking us very much less time than it takes us to measure half of a period of that waveform, or about 8.3 milliseconds. We can do that at near the velocity of light. But it takes the marrying of physics and that physics from the communications world, along with power systems, or that convergence, in order to achieve that greater speed.
When we look at convergence in one field, electronic and electrical engineering, we see that there are diverse aspects of what we have to learn in order to understand how we would solve problems. We can further build on that and realize that many diverse areas of the field of engineering rely on an understanding of that convergence of knowledge. So if we're working with people who design structures that hold our transmission lines, they would have a background in the mechanics of structures. We need to understand some of the limitations, requirements that they have, and we need to effectively communicate with them our needs and requirements. So we see a convergence of areas into a system, and systems become fundamental to us being able to solve problems in engineering. But there's even more. So this concept of convergence applies not just within a faculty such as engineering, but to the larger university community as a whole. So the expertise and knowledge that one particular unit may have, be it in liberal arts, be it in science, be it in engineering, is really of value only when we look at the whole convergence of skills that can be brought to solving a problem. So the critical thinking that's developed, regardless of what program you're in at the University of Regina, is of great value if it can be shared with other disciplines, both inside the university environment and in the greater world. So regardless of the program that you're studying in, I hope you have a great experience here at the University of Regina. Thank you.